Good day everyone. We are Group 2 and we are here to present a review of thermal science. In this presentation, we're going to discuss about thermal science, thermodynamics, heat transfer, fluid mechanics, thermochemistry, heat engines and power plants, and refrigerators and heat pumps. I am Mel Alfred Leccio and I'm here to discuss the first three topics. First is thermal science. What is thermal science? Thermal science is a branch of science concerned with heat and energy, specifically through thermodynamics and heat transfer. It is used in a variety of practical applications including heating systems, energy generation, and research. Thermal science is commonly regarded as a branch of engineering because it is most frequently used in a practical application by engineers attempting to design more safe and efficient heating and energy generation systems. Thermal science is an attempt to balance heat transfer and thermodynamic laws in order to generate energy more efficiently. As a scientists and engineers collaborate to use thermal energy more efficiently, thermal science incorporates several scientific disciplines all dealing with energy. Thermal science is concerned with finding new ways to extract heat, insulate energy, and use it in the most efficient way possible. Thermodynamics. What is thermodynamics? Thermodynamics is in its wider definition is concerned with the transfer of energy from one place to another and from one form to another. The fundamental idea is that heat is a type of energy that corresponds to a specific amount of mechanical work. The application of thermodynamics principle begins with the definition of a system that is distinct from its surrounding in some way. A sample of gas inside a cylinder with a movable piston, an entire steam engine, a marathon runner, the planet Earth, neutron star, black hole, or even the entire universe, for example, could be the system. In general, systems are unrestricted in their ability to exchange heat, work, and other types of energy with their surroundings. We have here Law of Thermodynamics. Zeroth Law of Thermodynamics. The zeroth law of thermodynamics states that if two bodies are in each thermal equilibrium with third body, then they are also equilibrium with each other. Thermal equilibrium means that when two bodies are brought into contact with each other and is separated by a barrier that is permeable to heat, there will be no transfer of heat from one to another. Next is first law of for thermodynamics. The first law of thermodynamics states that heat is a form of energy and thermodynamic processes are therefore subject to the principle of conservation of energy. This means that heat energy cannot be created or destroyed. It can, however, be transferred from one location to another and converted from one form to other forms of energy. Next is second law of thermodynamics. The second law of thermodynamics means that hot things will always cool unless you do something to stop them. It expresses a fundamental and simple truth about the universe, that disorder characterized as a quantity known as entropy always increases. Example is in a one-way process in nature is A. Heat transfer occurs spontaneously from heat to cold and not from cold to hot. And B is the brake of this car converts kinetic energy to heat to transfer to the environment. And the last is the burst of the burst of gas let into the vacuum chamber quickly expands to uniformly fill every part of the chamber. The random motion of the gas molecules will never return them to the corner. And last but not the least, third law of thermodynamics. The third law of thermodynamics is concerned with behavior of systems as the temperature approaches absolute zero. It relates heat and entropy at this ultimate lowest temperature for crystals, which refer to any solid material made up of atoms arranged in a definite symmetrical pattern. The third law of thermodynamics states that the entropy of a perfect crystal is zero when the temperature of crystal is equal to absolute zero or 0 Kelvin. According to the Purdue University, the crystal must be a perfect or else there will be some inherent disorder. Next we have energies. Energies are thermal or heat, chemical, nuclear, sound, light, radiant, and other forms of energy can exist, and the total energy of a system is the sum of this form. The microscopic energy refers to the types of energy associated with systems, molecular structure, and degree of molecular activity. Okay, so the internal energy of a system is defined as the sum of all microscopic forms of energy, and it is indicated by U. And then the international unit of energy is joule or kilojoule, which is 1 kilojoule is equals to 1000 joule. And the British thermal unit or BTU is the unit of energy in English system, and it is defined as the amount of energy required to raise the temperature of 1 pound of water from 60 to 1 degree Fahrenheit. Next we have, okay, we frequently find the combination of characteristic U and PV in the analysis of systems involving fluid flow. And this combination is defined as specific enthalpy or just enthalpy. PV stands for the fluid flows energy, also known as flow work, which is energy required to propel a fluid and keep it flowing. It is convenient to treat the flow of energy as a part of fluid's energy and to represent the microscopic energy of a fluid stream by enthalpy in the energy analysis of flowing fluids. And then, the energy required to raise the temperature of a unit mass of a substance by 1 degree is known as specific heat. Specific heat at constant volume and specific heat at constant pressure are the two types of specific heats that we are normally interested. The specific heat at constant pressure is higher than specific heat at constant volume because the system is permitted to expand at constant pressure, and the energy required for this expansion work must be also given to the system. These two specific temperatures are proportional for or perfect gases. Next we have energy transfer. Two, tech, two techniques can transfer energy to or from a given mass: heat transfer and work. Power is defined as the amount work done per unit of time and symbolizes by W. The unit of power, kilowatts or HP is equals to 1 HP is equals to 0.746 kilowatt. Q represent the quantity of heat transferred during the process. The heat transfer rate represented by Q over dot is the quantity of heat transported per time. The unit of heat transfer rate is kilojoule per second or British thermal unit per hour, which is equal to kilowatt. The rate of cooling provided by cooling equipment or cooling capacity is frequently represented in ton of refrigeration units. With 1 ton equaling to 12,000 British thermal unit per hour in cooling application. When the rate of heat is available, then the total amount of heat transferred during the interval can determine from Q is equals to integral function rate of heat between 0 and delta. For the special case, Q over that is equals to constant. The equation above reduces to Q is equals to rate of the heat multiplied by the delta T. Energy balance. Uh, for energy balance for a closed system has a constant mass. For most systems seen in practice, the total energy E is made up of internal energy U In such case, the energy balancing relation becomes E in minus EO is equals to U, or it is equals to MCV change of T, where the internal energy change in stated terms of mass, specific heat at constant volume, and temperature change of the system. The energy balance equation is further reduced to Q is equals to mCV change of T when the system just involves heat transfer and no work interaction across the boundary Q. Q is the net of or net amount of heat transfer to or from the system. When working with a fixed mass, this is the most common version of the energy balance relation. The rate of mass flow into the control volume must be equal to the rate of mass flow out in the steady flow system, with one inlet and one exit. When the variation of in kinetic and potential energies are small, they are generally are, and there is no work interaction. The energy balance for a steady flow system is Q is equals to M change of H, or it is equal to M C change of T, where the Q is the rate of net heat transfer into out of the control volume. Next we have saturation temperature and saturation pressure. The saturation temperature, or Tsat, is the temperature at which a pure material changes phase at a given pressure. Similarly, the saturation pressure, or Psat, is the pressure at which a pure substance changes phase at given temperature. Tsat is 100 degrees at a pressure of 101 3 kilopascals, and vice versa. Psat on the other hand is 101.3 kilopascal at a temperature of 100 degrees Celsius. Next we have heat transfer. Heat transfer refers to any of all of numerous of events that transport energy and entropy from one region to another and are considered mechanisms. Convection, thermal radiation, and conduction are terms used to describe the specific mechanics. First, we have conduction heat transfer. Conduction is the transfer of energy from highly energetic particles of a substance to less energetic particles nearby as a result of particle interaction. The rate of heat conduction through a medium is determined by the medium shape, thickness, and material, as well as the temperature difference across the medium. That is, Q con is equals to Ka T1 minus T2 over change of X, or it equals to negative Ka change of T over change of X, where the proportionality constant K represents the material's thermal conductivity, which is a measure of its capacity to conduct heat. The equation above is reduced to differential form in limiting situation of change of X is equals to 0, and it will be rate heat of conduction is equals to negative Ka times dt over dx. Next we have convection heat transfer. Convection is the transmission of heat energy between a surface and a flowing fluid of differing temperatures. A natural convection is created by buoyant forces caused by density difference in the fluid caused by temperature changes. When the fluid is heated, the density of a boundary layer changes, causing the fluid to rise and be replaced by a cooler fluid that also heats and rises. Free or natural convection is the term for this ongoing phenomenon. Forced convection is a kind of heat transfer that involves forcing fluids to circulate in order to decrease heat transfer. This can be done with a ceiling fan, a pump, a suction device, or something else entirely. We have here the formula for convection heat transfer. Q is equals to HCA times dt. Q is the heat of transfer per unit time. Hc is equals to convective heat transfer coefficient of the process. A is the heat transfer area of the surface. Dt is the temperature difference between the surface and the bulk fluid. Next we have radiation heat transfer. Heat is transferred through radiation in form of electromagnetic waves, which are mostly visible in the infrared spectrum. The heat agitation of bodies' constituent components causes it to emit radiation. Radiation is a volumetric phenomenon, which means that all solids, liquids, and gases emit, absorbs, or transmit to various degrees. However, for solids that are opaque to thermal radiation, such as metals, wood, rocks, radiation is usually considered as a surface phenomenon because the radiation emitted by the interior organs such as materials can never reach the surface, and the radiation incident on such bodies is usually absorbed within a few micrometer on the surface. Next we have is the radiation energy per unit time emitted by a black body is proportional to the fourth power of the absolute temperature and may be stated as Q is equals to sigma T raised to 4A using the Stefan-Boltzmann law. Next we have the Stefan-Boltzmann law can be written as Q is equals to epsilon sigma T raised to 4 times A for objects other than ideal black bodies, or we call gray bodies. The incident radiation, also known as irradiation, is partially reflected, absorbed, or transmitted by a gray body. Depending on the type of material and the temperature of the surface, the emissivity coefficient ranges from 0 to 1. And the last but not the least, net radiation loss rate. When an emissivity and surface area of a thermodynamic temperature is entirely contained by a considerably large or black surface at a thermodynamic temperature separated by a gas such as air that does not interfere with radiation, the net radiation heat loss rate of a hot object emitting energy to a cooler surroundings can be stated as Q is equals to epsilon sigma times Th raised to 4 minus Tc raised to 4 times A. And that is for the heat transfer.
So we have fluid mechanics. So first, what is mechanics? Mechanics is the oldest physical science that deals with both stationary and moving bodies under the influence of forces. There are two branches of mechanics. One is we have statics, which deals with bodies at rest, and dynamics, which deals with bodies in motion. So next, what is fluid mechanics? Fluid mechanics is the study of fluid behavior, liquids, gases, blood, and plasmas at rest and in motion. Fluid mechanics has a wide range of applications in mechanical and chemical engineering, in biological system, and in astrophysics. It is also the interaction of fluids with the solids or other fluids at the boundaries. So there are three subcategories for fluid mechanics. One we have is hydrodynamics. This is a study of the motion of fluids that can be approximated as incompressible. A subcategory of hydrodynamics is hydraulics. This deals with liquid flows in pipes and open channels. Next we have is gas dynamics, which deals with the flow of fluids that undergo significant density changes, such as the flow of gases through nozzles at high speeds. And last, we have aerodynamics. This deals with the flow of gases, especially air, over bodies such as aircraft, rockets, and automobiles at high or low speeds. Next, we have is characteristics of solid. Solids are rigid and have specific shapes and definite volumes. The atoms or molecules in a solid are in close proximity to each other, and there is a significant force between these molecules. Solids will take a form determined by the nature of these forces between the molecules. Although true solids are not incompressible, it nevertheless requires a large force to change the shape of a solid. So some solid can be compressible, but it takes a lot of force to do it. But main or true solids aren't that compressible, are not really compressible. It needs a large force to change their shapes. Next is we have solids will take a form determined by the nature of these forces between the molecules, as said earlier, which means that solids are, their shapes are what are, they don't change easily. Their shapes are consistent because of the molecules inside this particular object. So as you can see in the photo here, this is a photo of the molecules of a solid organized into a lattice. As you can see, they are connected and bonded to each other, which means that there is a limited movement or free space for these molecules to move. The structure of this three-dimensional lattice is represented as molecules connected by rigid bonds, which allow limited freedom for movement. Even a large force produces only small displacements in the atoms or molecules of this lattice, and the solid maintains its shapes. Solids also resist shearing forces. Next is the characteristics of fluids. Liquids and gases are considered to be fluids because they yield to shearing forces, whereas solids resist them. Like solids, the molecules in a liquid are bonded to neighboring molecules, but possess many fewer of these bonds. The molecules in a liquid are not locked in place and can move with respect to each other. The distance between molecules is similar to the distance in a solid, and so liquids have definite volumes, but the shape of a liquid changes depending on the shape of its container. Gases are not bonded to neighboring atoms and can have large separations between molecules. Gases have neither specific shapes nor definite volumes, since their molecules move to fill the container in which they are held. As you can see in the photo, the molecules in the liquid has a bit more bond compared to the gases, the molecules in the gases. So the molecules in the gases, they can freely move, and they also, similar to liquid, they also take the shape of the container because they can easily move. But the molecules in the liquid is more similar to that of the solid. So they have a definite volume like the solid. Liquids deform easily when stressed and do not spring back to their original shape once a force is removed. This occurs because the atoms or molecules in a liquid are free to slide about and change neighbors. That is, liquids flow with the molecules held together by mutual attraction. When a liquid is placed in a container with no lid, it remains in the container because the atoms are closely packed. Liquids like solids resist compression. An extremely large force is necessary to change the volume of a liquid. Oh, I'm sorry. In contrast, atoms and gases are separated by large distances, and the forces between atoms in a gas are therefore very weak, except when the atoms collide with one another. This makes gases relatively easier to compress and allows them to flow, which makes them fluids. When placed in an open container, gases, unlike liquids, will escape because of its molecules being able to move more freely. So density. Density is an important characteristic of substances. It is crucial, for example, in determining whether an object can sink or float in a liquid. Density is defined as mass per unit volume. Homogeneous materials such as iron or ice has the same density all throughout. The SI unit of density is kilograms per meter cube. In the given equation, we have the Greek letter rho, which is a symbol for density, m for mass, and V for volume. Pressure. Pressure is defined for all states of matter, but it is particularly important when discussing fluids. An important characteristic of fluids is that there is no significant resistance to the component of a force applied parallel to the surface of a fluid. The molecules of the fluid simply flow to accommodate the horizontal force. A force applied perpendicular to the surface compresses or expands the fluid. If you try to compress a fluid, you find that a reaction force develops at each point inside the fluid in the outward direction, balancing the force applied on the molecules at the boundary. So pressure is defined as a force per unit perpendicular area over which the force is applied. So the formula here that we have where P is a pressure at a particular depth, then we have F as a force over A as acceleration. The SI unit of pressure is the Pascal. 1 Pascal is equals to 1 Newton per meter squared. Pressure due to the weight of a liquid of constant density is given by pressure equals to rho times gravity times height, where P is the pressure, H is the depth of the liquid, rho is the density of the liquid, and G is acceleration due to gravity. So viscosity. So what is viscosity? Viscosity is the resistance of a fluid or liquid or gas to a change in shape of or movement of neighboring portions relative to one another. Viscosity denotes opposition to flow. So when two solid bodies in contact move relatively to each other, a friction force develops at the contact surface in the direction opposite to motion. So for example of this is honey. When you try to pour honey, the movement or the acceleration of the honey is slow compared if you try to move water. It moves smoothly and easily. It is because the viscosity of honey is different from the viscosity of water. The situation is similar when a fluid moves relative to a solid or when two fluids move relative to each other. We move with relative ease in air, but not so in water. That's an example. If you try to swim It's harder to walk in the pool than walk than just walking regularly. It's harder to move. You move harder in the pool. The viscosity of a fluid is a measure of its resistance to deformation. Viscosity is due to the internal frictional force that develops between different layers of fluids as they are forced to move relative to each other. So viscosity is again caused by the cohesive forces between the molecules in liquids and by the molecular collisions in gases. So what are Newtonian fluids? Newtonian fluids are fluids for which the rate of deformation is linearly proportional to the shear stress. So shear stress. Shear stress can be expressed by the linear relationship where the constant of proportionality mu is called the coefficient of viscosity or the dynamic viscosity of the fluid. So kinematic viscosity. In general, the viscosity of a fluid depends on both temperature and pressure. Although the dependence on pressure is rather weak, for liquids, both the dynamic and kinematic viscosities are practically independent of pressure, and any small variation with pressure is usually disregarded, except at extremely high pressures. For gases, this is also the case for dynamic viscosity, but not for kinematic viscosity, since the density of a gas is proportional to its pressure. So, what really is kinematic viscosity? Kinematic viscosity is the ratio of dynamic viscosity to density. Two common units of kinematic viscosities are meters squared per second and Stoke. 1 Stoke is equal to 1 centimeters squared per second, which is equal to 0.0001 meters squared per second. Pressure drop in fluid flow in pipes. The pressure loss and head loss for all types of internal flows, laminar or turbulent, in circular or non-circular pipes, smooth or rough surfaces, are expressed as the given equation in the PowerPoint, where ρ is the density, v is average velocity of fluid, L is the pipe length, g is gravitational acceleration, ρ v squared over 2 is the dynamic pressure, and the dimensionless quantity F is the friction factor. Poiseuille's law. This is also called as Hagen-Poiseuille flow. And this flow is in honor of the works of G. Hagen and J. Poiseuille on this specific subject. The pressure drop, which is change in pressure, delta P, and the volume, flow rate V, for laminar flow in a horizontal pipe. Sorry. Next is Colebrook equation. In fully developed turbulent flow, the friction factor depends on the Reynolds number and the relative roughness. The friction factor in turbulent flow is given by the given equation in the PowerPoint. So the plot of this formula is known as the Moody chart. An example is shown. This is an example of a Moody chart. Next is Churchill equation, an equation that was generated by Churchill that is not only explicit, but is also useful for any RE and any roughness, even for laminar flow, and even in the fuzzy transitional region between laminar and turbulent flow. The difference between the Colebrook and Churchill equations is less than 1% because it is explicit and valid over the entire range of Reynolds number and roughnesses. It is recommended also that the Churchill equation be used for determination of friction factor, or F. So here we have the required pumping power to overcome the pressure loss, where V is the volume flow rate and M is the mass flow rate. Next we have is thermochemistry. What is thermochemistry? Thermochemistry is defined as a branch of thermodynamics that focuses on changes occurring during chemical reactions. So these are thermochemical purposes. Chemical reactions are understood to include not only the reactions in which the products have a different chemical composition, but also those that result in a physical transformation. Fuels and combustion. Fuel is any material that can be burned to release thermal energy. Most familiar fuels consist primarily of hydrogen and carbon, and these are called hydrocarbon fuels. They are mostly denoted by the general formula C, N, or HM. Hydrocarbon fuels exist in all phases, some examples being coal, gasoline, and natural gas. The oxidizer mainly for this for combustion processes will be discussed later, but it is oxygen. We will further discuss regarding it later. The main constituent of coal is carbon. Coal also contains varying amounts of oxygen, hydrogen, nitrogen, sulfur, moisture, and ash. It is difficult to give an exact mass analysis for coal since its composition varies considerably from one geographical area to the next and even within the same geographical location. Most liquid hydrocarbon fuels are a mixture of numerous hydrocarbons and are obtained from crude oil by distillation. The most volatile hydrocarbons vaporize first, forming what we know as gasoline. The less volatile fuels obtained during distillation are kerosene, diesel, fuel, and fuel oil. The composition of a particular fuel depends on the source of the crude oil as well as on the refinery. Natural gas is produced from gas wells or oil wells rich in natural gas. It is composed mainly of methane, but also contains small amounts of ethane, propane, hydrogen, helium, carbon dioxide, nitrogen, hydrogen sulfate, and water vapor. On vehicles, it is stored either in the gas phase at pressures of 150 to 250 atmospheric pressure as CNG, compressed natural gas, or in liquid phase at negative 162 degrees Celsius as liquefied natural gas. LPG is a byproduct of natural gas processing or the crude oil refining. It consists mainly of propane, and thus LPG is usually referred to as propane. However, it also contains varying amounts of butane, propylene, and butylene. Propane is commonly used in fleet vehicles, taxis, school buses, and private cars. Ethanol is obtained from corn, grains, and organic waste. Methanol is produced mostly from natural gas, but it can also be obtained from coal and biomass. Both alcohols are commonly used as additives in oxygenated gasoline and formulated fuels to reduce air pollution. So, combustion. What is combustion? Combustion is a chemical reaction during which a fuel is oxidized and a large quantity of energy is released. So the oxidizer most often used in combustion process is air. So why is that? On a mole or a volume basis, dry air is composed of 20.9% oxygen, 78.1% nitrogen, 0.9% air, and small amounts of CO2, helium, neon, and hydrogen. So in this analysis, the argon in the air is treated as nitrogen, and the gases that exist in trace amounts are disregarded. So making the composition of dry air approximated as 21% oxygen and 79% nitrogen by mole numbers. Each mole of oxygen entering a combustion chamber is accompanied by 0.79 over 0.21 or 3.76 mole of nitrogen. During combustion, the fuel must be brought above its ignition temperature to start the combustion. The minimum ignition temperatures in atmospheric air are approximately 260 degrees Celsius for gasoline, 400 degrees Celsius for carbon, 580 degrees Celsius for hydrogen, 610 degrees Celsius for carbon monoxide, and 630 degrees Celsius for methane. Proportions of the fuel and air must be in the proper range for combustion to begin. For example, natural gas does not burn in air in concentrations less than 5% or greater than about 15%. For most combustion processes, the moisture in the air and the H2O that forms during combustion can also be treated as an inert gas, like nitrogen. At very high temperatures, however, water vapor dissociates into hydrogen and oxygen as well as into HO and OH. So during combustion process, the components that exist before the reaction are called reactants, and the components that exist after the reaction are called products. So it is also important to be able to predict the dew point temperature, since the water droplets often combine with the sulfur dioxide that may be present in the combustion gases, forming sulfuric acid, which is highly corrosive. So when the combustion gases are cooled down below the dew point temperature of the water vapor, this is when sulfuric acid or acid rain may occur because some moisture condenses into the air. Air-fuel ratio, AF, is usually expressed as a mass basis and is defined as the ratio of the mass to air to the mass of fuel for a combustion process. Theoretical and actual combustion processes. So we have the two types of combustion. One is complete combustion. In this combustion, all the carbon in the fuel burns to carbon dioxide and all the hydrogen burns to H2O, and all the sulfur, if any, burns to SO2 or sulfur dioxide, I'm sorry. While in incomplete combustion, if the combustion products contain any unburned fuel or components, such as what are stated on the PowerPoint, this is when incomplete combustion occurs. So what are the reasons why there is incomplete combustions? There are three. We have insufficient oxygen, insufficient mixing in the combustion chamber during the limited time that the fuel and the oxygen are in contact. Then lastly is dissociation. Stoichiometric or theoretical air. This is the minimum amount of air needed for the complete combustion of a fuel. It is also referred to as chemically correct amount of air or 100% theoretical air. Next, we have is stoichiometric or theoretical combustion. This is the ideal combustion process during which a fuel is burned completely with theoretical air. So the minimum, when a fuel is completely burned with theoretical air or no uncombined oxygen is present in the product, this is when the theoretical combustion occurs. A combustion process with less than the theoretical air is bound to be incomplete. The ideal combustion process during which a fuel is burned completely with theoretical air is again called the theoretical combustion. Enthalpy of formation and enthalpy of combustion. Disregarding any changes in kinetic and potential energies, the energy change of a system during a chemical reaction is due to a change in state and a change in chemical combustion. So this is delta E system is equal to delta E state plus delta E chemical. So, and what is enthalpy of reaction or HR? This is the difference between the enthalpy of the products at the specified state and the enthalpy of the reactants at the same state for complete reaction. Enthalpy of combustion. It is the enthalpy of reaction for combustion process. It represents the amount of heat released during a steady flow combustion process when 1 kmol or 1 kilogram of fuel is burned completely at a specific temperature and pressure. The formation of CO2 during a steady flow combustion process is at 25 degrees Celsius and 1 atmospheric pressure. Also, to establish a starting point, we assign the enthalpy of formation, which is, what is the enthalpy of formation? Skip here. This is the enthalpy of a substance at a specified state due to its chemical composition. So we assign the enthalpy of formation of all stable elements a value of 0 at the standard reference state of 25 degrees Celsius and 1 atmospheric pressure. So what is the enthalpy of combustion? It also for combustion processes as well, the enthalpy of reaction is usually referred to as the enthalpy of combustion, which represents amount of heat released during a steady flow combustion process when 1 kmol of fuel is burned completely at a specified pressure, temperature, and pressure. Heating value. I'm sorry. Oh, let's explain the photo that we have here. So we have the combustion process, the figure here with the combustion process or the combustion chamber. The enthalpy of a combustion represents amount of energy released as a fuel is burned during a steady flow process at the specified state. So heating value is the amount of heat released when the fuel is burned completely in a steady flow state process and the products are returned to the state of the reactants. The heating value of fuel is equal to the absolute value of the enthalpy of the combustion fuel. So what is, we have here higher heating value, HHV, when the H2O in the products is in the liquid form. Lower heating value when the H2O in the products is in the vapor form. So what is the relationship between HHV and LLV? We have here HHV is equals to LHV plus MH, quantity MH, H2O. For the fuels with variable composition, the heating value may be determined by burning them directly in a bomb calorimeter. The heating value of a fuel is equal to the sum of the lower heating value, as stated here, and the latent heat of vaporization of H2O in the product. So that is what our equation states. So the first law analysis of reacting systems. The energy balance, or the first law relations, is applicable to both reacting and non-reacting systems. However, chemically reacting systems involve changes in their chemical energy, and thus it is more convenient to rewrite the energy balance relations so that the changes in chemical energies are explicitly expressed. So when the changes in kinetic and potential energies are negligible, the steady flow energy balance for a chemically reacting steady flow system is here. This is the equation. So the first equation here, pointer, let's use the pointer. Oh. Here, this part, this is the rate of net energy transfer in by heat, work, and mass. While this one, this is the rate of net energy transfer out by heat, work, and mass. For this, for the equation below, this side, it is the energy transfer in per mole of heat per mole of fuel by heat, work, and mass. While this one, it is the energy transfer out per mole of fuel by heat, work, and mass. The enthalpy of a chemical component at a specified state is the sum of the enthalpy of the component at 25 degrees Celsius and the sensible enthalpy of the component relative to 25 degrees Celsius, 1 atmospheric pressure. So combustion chamber, a combustion chamber normally involves heat output but no heat input. Then the energy balance for a typical steady flow combustion process becomes, so this one is most steady flow, again, most steady flow combustion processes do not involve any work interactions. Therefore, a combustion chamber which does not involve heat output but no heat input, which involves heat output but no heat input. It is combustion chamber normally involves, this is the formula for that, and this one, this side, is energy in by mass per mole of fuel, while this is energy out by mass per mole of fuel. So that is it for the thermochemistry.
Good day, everyone. I'm Divine Garcia, and I'm here to discuss about heat engines and power plants. Work can easily be converted to other forms of energy, but converting other forms of energy to work is not that easy. Work can be converted to heat directly and completely. However, converting heat to work requires the use of some special devices, and these special devices are called heat engines. Heat engines differ considerably from one another, but all can be characterized by the following. Number one, they receive heat from a high temperature source, like solar energy and nuclear reactor. Number two, they convert part of this heat to work, and it is usually in the form of a rotating shaft. Number three, they reject the remaining waste heat to a low temperature sink. An example of a low temperature sink is the atmosphere and rivers. Number four, they operate on a cycle. As shown in the figure, we can say that part of the heat received by a heat engine is converted to work, while the rest is rejected to the sink. Next is the steam power plant. A steam power plant is a work-producing device that best fits into the definition of a heat engine. Aside from that, steam power plant is an external combustion engine. In here, the combustion takes place outside the engine, and the thermal energy released during this process is transferred to the steam as heat. Next is the schematic of a basic steam power plant. The various quantities shown on this figure are as follows. Q in is the amount of heat supplied to steam in the boiler from a high temperature source. Q out is the amount of heat rejected from steam in the condenser to a low temperature sink. W out is the amount of work delivered by steam as it expands in the turbine. W in is the amount of work required to compress water to the boiler pressure. Notice that the directions of the heat and work interactions are indicated by subscripts in and out. Therefore, all of the described quantities are always positive. The network output of this power plant is simply the difference between the total work output of the plant and the total work input. Next. As shown in the figure, no mass enters or leaves this combination system. It can be analyzed as a closed system. A closed system undergoing a cycle, the change in internal energy is zero, and therefore, the network output of the system is also equal to the net heat transfer to the system. Next. Next is the thermal efficiency. It is the measure of how efficiently a heat engine converts the heat that it receives to work. It is also defined as the fraction of the heat input that is converted to network output is a measure of the performance of a heat engine. Heat engines are built for the purpose of converting heat to work, and engineers are constantly trying to improve the efficiencies of these devices, since increased efficiency means less fuel consumption and thus lower fuel bills and less pollution. The thermal efficiency of a heat engine can be expressed as efficiency equals the net work output over the total amount of heat input by fuel. Using net power and the rate of heat input, efficiency is equals to the net power output all over the total rate of heat input by fuel. It can also be expressed as the efficiency equals 1 minus Q out over Q in. Next is the Carnot cycle. It is the most efficient heat engine cycle because number 1, it is the perfect engine. Number 2, processes are reversible. Number 3, thermal capacity of heat source and heat sinks is infinite. To further explain Carnot cycle, let me play a short animation video for you.
In 1824, Sadi Carnot designed a theoretical heat engine whose working efficiency was 100%. Heat engines are devices that can convert heat into mechanical energy, like a steam engine or motor vehicle. The working principle of all heat engines are the same, in which any working substance, gas or vapor, is brought back to the initial stage by going through different thermodynamic stages of a cyclic process. Carnot suggested that if a heat engine goes through fixed thermodynamic stages of a specified process, then the efficiency of the heat engine may be 100% possible. This is called the Carnot engine or ideal heat engine. Why ideal heat engine? Because this engine gives maximum efficiency. No other engine can be more efficient than this. This specified cyclic process suggested by the Carnot is called Carnot cycle. The Carnot engine has three main parts. First, an insulated non-conducting stand, so that the transfer of energy is not possible. Second, a hot reservoir with infinite heat capacity. Heat capacity is infinite so that the temperature of the reservoir remains constant after taking any amount of energy from it. It is also called heat source. Third, a cold reservoir. Its heat capacity is also infinite, so that any amount of heat is given, its temperature does not change. This is called heat sink. Fourth, a cylinder in which the working substance can be kept. Working substance can be anything, gas or liquid. The cylinder is fitted with a movable piston. The piston and the cylinder walls are made up of non-conducting material, due to which transfer of heat is not possible, while the base of the cylinder is conducting. The Carnot engine goes through 4 different stages of the Carnot cycle, which is graphically displayed on a PV graph. For this, first place the cylinder on the hot reservoir. Since the temperature of the reservoir is higher than the temperature of the gas, the heat flows from the hot reservoir to the gas, due to which the gas starts to expand. Since due to heat transfer gas is expanding, therefore the temperature of the gas remains constant. This process is called isothermal expansion. As the gas expands, the volume of the gas increases and the pressure decreases. The next step, take off the cylinder from the hot reservoir and place it on the insulating stand. When doing so, the gas is confined to the non-conducting wall. Now let piston rise slowly upward, due to which the gas continues to expand. But this time the gas is not getting any amount of heat to expand. Such expansion is called adiabatic expansion. Since this expansion is taking place without heat, the temperature of the gas starts to decrease. Due to this expansion, the volume of the gas also increases and the pressure decreases. Next step, lift the cylinder from the stand and place it on the cold reservoir. Now press the piston downward, which causes compression of the gas. The reservoir absorbs whatever extra heat is produced due to the compression of the gas. In this way, the gas compresses at the same constant temperature. The process is called isothermal compression. Due to this compression, the volume of the gas decreases and the pressure is increased. In the final step, Again, keeping the cylinder on the stand and press the piston downward. But now there is no cold reservoir to absorb the heat getting produced extra. Therefore, the temperature of the gas starts increasing. This compression is called adiabatic compression. Press the piston until the temperature of the gas rises back to equal that of the hot reservoir. This decreases the volume of the gas and increases the pressure. At the end of this step, the gas returns to its initial stage. This complete cycle is called the Carnot cycle, and the engine working on it is called the Carnot engine. The efficiency of a Carnot engine depends on the temperature of the both reservoirs. Either raise the temperature of the hot reservoir to infinite Kelvin or lower down the temperature of the cold reservoir to 0 Kelvin. In both cases, the efficiency will be 100%, but it is not possible to do so. Hence, the Carnot engine is just a theoretical ideal engine. To increase the efficiency of a practical engine, we keep as much as difference as possible in the temperature of both reservoirs.
That's all for the Carnot cycle. Next is the overall plant efficiency. The overall plant efficiency can be used to express the performance of all power plants which burn a fuel, such as steam power plants, gas turbine power plants, and automobile engines. Note that the thermal efficiency and overall plant efficiency are sometimes used interchangeably. We may define an overall plant efficiency based on the total energy of the fuel consumed in the plant, where W net out is expressed in kilojoules, and it is the network output of the plant. M fuel is expressed in kilograms, and it is the amount of fuel consumed. And HV fuel is expressed in kilojoules over kilograms, and it is the heating value of the fuel. Now for the refrigerators and heat pumps. Refrigerators are cyclic devices, and the working fluids used in the refrigeration cycles are called refrigerants. Another device is the heat pumps. It is the device that transfers thermal energy between spaces, usually between an enclosed space and the outdoors. It is also defined as a device that transfers heat from a low temperature medium to a high temperature. Refrigerators and heat pumps are essentially the same devices. They differ in their objectives only. The objective of a refrigerator is to maintain the refrigerated space at a low temperature by removing heat from it. Discharging this heat to a higher temperature medium is merely a necessary part of the operation, not the purpose. The objective of a heat pump, however, is to maintain a heated space at a high temperature. Now for the coefficient of performance, or the COP. The coefficient of performance is an expression of the efficiency of the system, where Q is the useful heat supplied or removed by the considered system. W is greater than 0, and it is the network put into the considered system in one cycle. Higher COPs equate to higher efficiency, lower energy consumption, and thus lower operating cost. The COP usually exceeds 1, especially in heat pumps, because instead of just converting work to heat, it pumps additional heat from a heat source to where the heat is required. Now for the Carnot refrigerators and heat pumps. The most efficient refrigeration and heat pump cycles are referred to as a Carnot refrigerators and heat pumps, which consist of a totally reversible processes. The coefficients of performance of a Carnot refrigerator and heat pumps can be expressed in terms of temperature as shown in the slide. This conclusion is also applicable to actual refrigerators and heat pumps. The reversed Carnot cycle is the most efficient refrigeration. refrigeration cycle, operating between two specified temperatures. The reverse Carnot cycle cannot be approximated in an actual devices, and it is not realistic model for our refrigeration cycles. However, the reverse Carnot cycle can be served as a standard against which actual refrigeration cycles are compared. That's all for our report, and we hope that you learned a lot. Thank you.